Yes,
Okay.
so welcome to everyone. A reminder to please, unless you're speaking, keep yourself muted. If you have questions, please type them in the chat. And our first speaker is Tucker McElroy from the U.S. Census Bureau on identifying seasonality. And Brian posted a link to the paper in the chat. All right, thanks, Tucker. Go ahead.
Great. So the presentation is a tutorial based on a report of the same name. And these are the co-authors of that report. So the introduction, I'll be talking about seasonal adjustment, the process of removing seasonal patterns from time series data. And we can think about 3 steps. First, determine if the time series is seasonal. If it's not, stop. You don't do anything more. Second, if time series is seasonal, then perform seasonal adjustment. Third step, if we want to determine if that seasonal adjustment is adequate. If it's not, if it is, then you can stop and you're done. If it's not, then you have to go back to step 2, try to modify the seasonal adjustment, maybe choose a different model or alter the program options, and you will continue the process until you obtain adequate seasonal adjustment. It can happen that no seasonal adjustment is acceptable or adequate. Then you could decide not to adjust the series or accept an inadequate adjustment. So one of the some of the important tools for determining adequacy, and well, actually all the steps of this process would be graphs, hypothesis tests, and also other statistical diagnostics. In step 3, what we're trying to do is assess whether residual seasonality, RS, is present in the data that we've already seasonally adjusted. And we'd like to have no RS. So in this presentation, the main goals, or at least for my part, I'll go through and document the seasonality diagnostics that are available in the Census Bureau's X13 REMA Seats software. So it kind of has a narrow focus on that particular piece of software. I'll provide some illustrations to time series data, and Kathy's part, she'll go into those examples in a lot more detail. I'll look at the examination of testing for seasonality in the unadjusted series. So that's the first part, step 1, that's called pretesting. And then also looking for residual seasonality in step 3, and that's called post-testing. So it's pre and post, before and after the seasonal adjustment process. So we typically use the same diagnostics, the same mathematical tools for both unadjusted series in step 1 and also for adjusted series in step 3. Even though there's the time series before and after have different statistical properties. So the diagnostics can also, in step 3, can also be applied to the irregular component or to model residuals. So typically the main differences between these types of applications are in the data span, like how much of the time series sample you want to use. And it's a bit of a common practice to use the same diagnostics, even though it might be more cosmetically pleasing to have different diagnostics for pre-testing and post-testing, because they're different statistical problems. Okay, so outline. Basically, I'll begin with a discussion of direct and indirect seasonal adjustment methods. I'm not going into a lot of detail on these points. I'm just sort of giving a bird's eye view of everything. Second, a description of some common software for seasonal adjustment. Again, I'll be narrowly focused on Census Bureau software. Then a description of seasonality diagnostics that we have available. And finally, I'll go through a few examples, and Kathy will flesh those out. Okay, so first is the discussion of direct and indirect. So most published series in official statistics are components of some greater aggregate. Typically, there's a hierarchical structure to the time series data that's published. So it's pretty natural to study seasonal adjustment adequacy on batches of related series. So direct adjustment, the idea is that you have an aggregate time series higher in the hierarchy, and you would just seasonally adjust that without respecting its accounting relations or aggregation relations to its subcomponents. So heuristically, you think of I would sum those component series and then adjust the sum. Indirect, on the other hand, you look at this aggregate time series and you'll get its seasonal adjustment by summing up the seasonal adjustments of the components. So there, the idea is that you adjust first the components and then you add up. So there's pros and cons of these approaches. The aggregation here is typically summation, just like adding up. Like, for example, you might have motor vehicle sales and then it's broken up into motorcycles and RVs. And so you can sum those two to get the higher aggregate. But another type of aggregation that can happen is cross sampling frequency, where you sum up monthly values to get quarterly values. So it can happen that many components exhibit no seasonality in the pretest phase, and yet when we aggregate, we get a series that does have seasonality. And this is kind of maybe it's a little bit non-intuitive, but some papers have been written that demonstrate how this could happen and empirically show that it does happen from time to time. So as a result, the indirect seasonal adjustment could very well have residual seasonality. So that's a problem. So what do we do? You can instead do direct seasonal adjustments. Some people have advocated this, but then the accounting relations are going to be violated. You could try to modify the models for each component time series, essentially trying to tweak their seasonal adjustment and hope that their aggregate would then have no seasonality, essentially that the RS problem would go away from the indirect adjustment. But there's really no guarantee that that would work. And then third is sort of just a more nuanced or intricate approach to that idea. We could try to modify the component seasonal adjustments as little as possible, but such that their aggregate has no seasonality, and that would require some numerical optimization. We're doing some research projects on this right now, but it's not been incorporated in the software. So again, just a bird's eye view of direct versus indirect. And so next I'd like to talk about seasonal adjustment software. The X11 method as implemented in the X13AS software. This procedure goes back to the 50s and 60s. Stats Canada enhanced the method in the 70s with the addition of remodeling for forecast extension. The basic procedure separates time series into trend cycle, seasonal, and irregular using iterative filtering, either working on the original data or it's possibly transformed with a log transform. And there's also involved removal of outliers. So moving averages are the technique that's used, and that's what we mean when we refer to filters. So the users can choose these moving average filters from a set of fixed pre-coded options, but there's also defaults that the software will use if none are selected by the user. So the software has an X11 specification that uses this method. The other kind of specification available is the seats method. Seats refers to a seasonal adjustment part of a broader program called Tramo Seats. This was developed by Agustin Maravall and Victor Gomez at the Bank of Spain. So Tramo does the modeling part using regression REMA models. So the regression parts allow you to model outlier effects, calendar effects, and other kinds of fixed effects, whereas the REMA part handles everything that's not deterministic and has some kind of stochastic variation to it. So Seats then uses these fitted models and it breaks them into models for the components, which are unobserved components. Now, when I say components here, I'm not talking about the components in a hierarchy like I was a couple of slides ago, but here we mean components would be like the seasonal component, the trend cycle component, and the irregular component. So there's this beautiful method called the canonical REMA decomposition, which finds models for those components and then derives filters to then extract them. So it gets to the same endpoint as the X11 method, namely by estimating components, unobserved components, but it uses a pretty different methodology. Okay, so, and there's lots of other software out there on the internet, and different agencies have different methods, but we were just sort of really focused on the software that was available for X13 REMA Seats, because that's sort of the scope of our document and our tutorial. So going on to diagnostics, for identifying seasonality, first you would just try to graph the time series. It can be very useful. You would graph the time series across consecutive time points. You can also do a year over year. That can help elucidate whether there's a seasonal pattern. And you can also find whether there's subspans that have some unusual behavior, such as extremes. Second is to look at the autocorrelation function of both the original and the difference time series. Difference refers to taking present value minus previous. And ACF plot helps to assess dependence in the time series, especially seasonal dependence. So it's a plot which has on the x-axis the lag of the effect, and on the y-axis is the amount of correlation. So for monthly data, a yearly effect would happen at lag 12 every 12 months. So one would focus on multiples of 12 and see if the correlation is high at those lags. For quarterly, we instead be looking at lags 4, 8, and 12. So this is large positive seasonal lag correlations are necessary, but not sufficient to indicate presence of seasonality. Conversely, if you have small correlations, then that'd be a lack of evidence of seasonality. So now I'll discuss 3 specific diagnostics present in the software: model-based F-test, the QS diagnostic of Maravall, and also looking at spectral plots and peaks and seasonal frequencies. So first, the model-based F-test, it checks for evidence of a stable seasonal pattern, and it's really designed for pretesting. You can apply it in the third step to look for residual seasonality, but there we would recommend using a subspan. It does require one to build an REMA model, since it's based on looking at regression coefficients in a reg REMA model. So for instance, if you had a SEREMA PDQ 011 that's already been fitted, Well, if you're familiar with stream models, this kind of model can be sort of close to an ARIMA PDQ with fixed seasonal regressors, potentially. And so that's one way of building that test statistic. So it does require the user to go and build a model first. So how it works, basically, the null hypothesis is that the coefficients of the fixed seasonal regressors are 0, i.e. that there's no fixed seasonality. So rejections of that null say that there is stable seasonality, a fixed seasonal pattern. And these results will depend upon the parameters of your fitted model and also the specification of that model. So here's just a running example I have for this part of the talk. U.S. retail sales of office supply, stationery, and gift stores. And this little graph or table is straight from the output. So here you have the regressor, the degrees of freedom, the F statistic, and in this case, p-values quite small, indicating rejection of the null. I haven't shown you the data yet, so this is the data here. This series plotted from 2002 to 2018, and these big spikes in December are recurring. So there's a strong seasonal pattern. It does change a bit over time, but there's also sort of a fixed seasonal component, which is what the model-based F test is indicating. Here's a plot of the series by each month. So each blue line there represents one single year from January through December. And you can see the big movements in December. So this is often a useful way to plot things and quickly visualize what's going on. Right, so the next guy to talk about is the QS. And here we look at the first two seasonal lag autocorrelations with large positive values indicating seasonality may be present. We focus on lags 12 and 24 for monthly data, 4 and 8 for quarterly. The basic null hypothesis is that the first two seasonal autocorrelations are 0. That would correspond to the series not being seasonal at all. And so rationale is that if there's no seasonality, you shouldn't really have positive autocorrelation at those lags. So how it works is the series will be different to remove trend effects, and we compute sample autocorrelations. If the first seasonal autocorrelation is 0 or negative, we just set QS to 0. Otherwise, it's a linear combination of these squared. Basically, we square those two sample autocorrelations. They're normalized by a factor and then added up. There's a heuristic chi-square distribution for that under the null, which is used to get the p-values. So some caveats. Any small degree of seasonal lag autocorrelation would be flagged as seasonal. Sometimes we don't like this because even if you have just a very, very mild amount of seasonality, QS is going to identify that and flag it. So for that reason, it's really better suited in the third post-testing step for detecting residual seasonality. Because in pretesting, sometimes we have series of a very mild degree of seasonality, and we might decide that it doesn't really need to be seasonally adjusted, but in that case, QS could still flag it. And so there's some applications you can apply it to the original series and also to the residuals from fitting a model, the irregular, and so forth. Some remarks. So we could
2 minutes, Tucker.
Okay, great. We can run QS on a subspan if there's concerns about sudden changes. Now, the QS diagnostics on each of these components, such as the irregular, the seasonal adjustment, and so on, they could be different. Usually, typically the most important component to focus on is the seasonally adjusted component. Yes, similar, same example as before, just applying this QS. In this case, the null of no seasonality is rejected, so there is seasonality in pretesting. And then secondly, examining the residuals and so forth, we get that there's failure to reject, so that's saying the seasonal adjustment is adequate. Here's the chart. Just focus on the first part here where it's got the full series. First two rows, you see that, QS has these large values for the original series and p-value is 0. Okay, so there's seasonality. Then when we go down to row 4 of the seasonally adjusted series, now the p-value is 0.9995, saying, okay, the seasonality has been removed. There's some additional output. I won't go over this. So let me talk finally about spectral peaks at seasonal frequencies. This is a graphical technique for identifying periodic patterns. To compute the so-called spectrum, you want at least 8 years of data. And then on the x-axis of the spectral plot, you have these frequencies, and the seasonal frequencies correspond to multiples of 1/12, and sort of the number of seasonal effects that occur each year. So we're looking for large peaks in this graph, and that would correspond to evidence of seasonality. How big do they have to be? Well, there's this idea of a 6-star criterion where a peak is bigger than its 2 nearest neighbors by at least 6 stars, where a star is a unit of measure equal to 1/52nd of the whole range. There's also, this is a little bit of information just about trading day frequencies can also be located on these plots, but I'm not going to say anything about that. So we can apply this method to the original series, to model residuals, and so forth. So there's lots of possible plots one can look at. So if any of the first 4 seasonal frequencies is visually significant, then seasonality might be there. Usually the 5th and 6th frequencies are ignored, and users may want to have at least 2 peaks being significant in order to flag seasonality. You can use this as both the pretest and a post-test, although seasonal adjustments typically have troughs at seasonal frequencies rather than peaks. So this example, same series, the first figure is the plot for the original series doing a pretest, and then there's a second figure based on a different graphical output, and then finally look at the seasonal adjustment. So this is really old school. This is the plot from the old ASCII output for the software, and so you can see the peaks are coming at those 6 seasonal frequencies marked with S's. And then this is essentially the same information in a prettier display. So the S's are marked there, and red lines for trading day. So on the other hand, this is for the seasonally adjusted series, and now at those seasonal frequencies marked with kind of pink lines, we see that there's not a peak anymore. So that's consistent with the idea that the seasonal adjustment has been adequate. I should be wrapping up real soon. So there's also table output here, which would just indicate, this tells you that the first 5 peaks are visually significant. The residuals have like a really weak peak, and so that's marked there. So finally, just a few remarks on pretesting and post-testing before I turn things over to Kathy. So the model-based F examines something a bit different from the QS and spectral diagnostics. It's looking at fixed seasonal pattern. A lot of times seasonality is evolving over time, and there may be a fixed component underlying that evolution. So detection of a fixed seasonal pattern is a very strong indication of seasonality. QS and spectral diagnostics are looking at seasonal dependence in the form of autocorrelation or through the spectrum. If there is fixed seasonal effects, they will tend to flag that, and you'll get large correlations and peaks. but they are also useful for detecting very mild or moderate degrees of seasonality. So they can be really much more appropriate for post-testing. For pre-testing, the model-based F is more useful than the QS and Spectral. So a significant post-test result might indicate a need to modify the underlying model or modify the seasonal adjustment options to find settings that more thoroughly remove seasonal effects. Yeah, and I think I'm all done. So thank you, and I will turn things over to Kathy.